Have you ever wondered how to compute the number of trainable weights in a convolution layer of a deep neural network? Let's figure it out together. So first, let me draw the simplest convolutional layer. Okay, we have a two-dimensional input image. Let's define, just using generic variables, the height being A, the width as B. And then we've got our output feature map. And again, generically, I'm going to define the height to be C and the width to be D. Note that A and B don't have to be equal, C and D don't have to be equal, but in many cases they might be. Then we also have a kernel size. So the convolution typically happens with a square kernel of size k by k. Now here's the trick. In terms of the number of weights for a convolution layer, do we care about the values of A, B, C, or D? The answer is no. Those values do not affect the number of weights because we're passing the kernel over the entire image. C and D are dependent on A and B and the values of k, but in terms of assessing the size of the red kernel here, the number of weights would simply be k times k plus 1. The 1 is for the bias. Now let's take this one step further. Suppose that we didn't have two-dimensional input, but instead our input was three-dimensional. Let's define that third dimension as E, the number of layers of our input. How does this change the number of weights in the convolutional operation? Well, the kernel now becomes three-dimensional. So the total number of weights is k times E, the number of layers here, plus 1 for the bias. Let's take it one step even further. What if our output feature map was not two-dimensional? In other words, what if we didn't want a single kernel for convolution, but we wanted multiple kernels, each generating their own feature map? What would that look like? We could have any number of feature maps here. I'm going to define this dimension as F, only because we're following through the alphabet, A, B, C, D, E, F. How does this affect the number of weights? Well, the number that we had previously simply gets multiplied by F. Each of the feature maps needs a three-dimensional kernel based on the three-dimensional input plus a bias term. Let's put some numbers to this. Suppose our input was 400 by 600. The number of kernels is 32. The size of each kernel is 3 by 3. Therefore, evaluating this expression, note that the 400 and 600 do not impact the number of weights. They simply impact the size of the feature maps at the next layer. So plugging in the values here, we have, and the total number of weights for this convolutional layer is 320. What if that input was three-dimensional? And the third dimension, let's assume that these are color images. Maybe it was the RGB layers. How would that impact the weights? Well, this 1 would become a 3. So that's 3 times 3 times 3 plus 1 times 32. And that would be 896 total weights. What about padding? What about the stride? Do those impact the number of weights? The answer is no. They simply impact the size of the feature maps generated by the convolution. All right, let's take this just one step further. In a deep network, we're not just going to have one convolutional layer. We might have multiple. If I wanted to compute the number of weights in this purple layer, how would I do that? Well, keep in mind that the size of the input here, which is the feature maps CD, and the size of the output feature maps, which don't have a label here, it would be like HI, those dimensions don't matter. They do not affect the number of weights in the purple convolutional layer. The only thing that matters would be the size of the kernel and the number of kernels, which determines the number of feature maps. So I'm showing the size of the kernel here as K2 and the number of feature maps as G. So now if I was to compute a similar equation as I did before, notice how the variables, some of them will change. We have shifted the role of F. It now takes on the role that E had previously. It's the number of input feature maps. And then G, the number of output feature maps, is the multiplier in this case. And that's how you figure out how many weights are in a convolutional layer of a deep neural network.